So let's go over the idea of analysis of variance. So the ideas of ANOVA can be a little bit daunting. I'll show them to you at the end of this chapter. But the main idea of ANOVA is more accessible and much more important. And that is when we ask whether a set of sample means gives evidence for differences among population means, what matters is not how far apart the sample means are, but how far apart they are relative to the variability of individual observations. So analysis of variance, we're looking at the variability. So here's the main idea. Analysis of variance compares variation due to specific sources with the variation among individuals that should be similar. In particular, ANOVA tests whether several populations have the same mean by comparing how far apart the sample means are with how much variation there is in the samples. So let's take a look at a visualization. So the sample means for the three samples are the same for each set A and B below. So all the sample means are the same. You can kind of see that they match up. Let me clear that though for clarity. The variation among sample means for A is identical to that for B, right? Because they have the same means. These means match up. But the variation among the individuals within the three samples is much less for B. So like B has less variation because its data is less spread out than that in A. So we can conclude the samples in B contain a larger amount of variation among the sample means relative to the amount of variation within the samples. So ANOVA will find more significant differences among the means in B. And we assume that they're equal sizes here. And, always keep in mind that larger samples reveal more significant differences. So how did I calculate that F statistic earlier? I am so glad you want to know. So one of the oddities of statistical language is that methods for comparing means are named after the variance. This is because the tests work by comparing the two types of variation we discussed in the previous slide. ANOVA is a general method for setting source of variation in responses. And we compare several means in the simplest form of ANOVA that we're focusing on, which is one-way ANOVA. So we calculate an F statistic, and this is our F is the variation among the sample means divided by the variation among individuals in the sample. So F must be 0 or positive, with F being 0 only when all sample means are identical, and with F getting larger as the means move further and further apart. Large values of F are evidence against our null hypothesis, which is all the means are equal, and our alternate hypothesis is many-sided, so there's at least one difference. But our F test is upper and one-sided. It's only positive. It's greater than 0 or greater. So in order to conduct an ANOVA test, we have to have some specific circumstances, like all inference procedures. So what we need to have independent simple random samples, one from each of a set number of I populations. The ith population has a normal distribution with unknown mean, and one way ANOVA is always going to test the null hypothesis that all means are the same. Key takeaway. We also assume that all of the populations have the same standard deviation whose value is unknown. And if we don't draw simple random samples that are separate from our population or carried out a randomized comparative experiment, the population to which the conclusions of inference apply may be unclear. So we want to check the results of the ANOVA test are approximately correct when the largest sample standard deviation is no more than twice as large as the smallest sample standard deviation. So we want our largest sample standard deviation to be no more than twice as big as our smallest. So I told you our ANOVA test has this form. To find the p-value for this statistic, we must know the sampling distribution of F when all the means are true, well, when all the means are equal, so our null hypothesis is true. And the distribution of this is an F distribution. The degrees of freedom for an Anova test depend on the number of means we're comparing and on the number of observations in the sample. So F test takes into account the number of observations. Careful that changing the degrees of freedom changes the distribution, so the order is important. So how do I figure out the degrees of freedom? So glad you asked. So what we want to do is we want to compare the simple random samples of the means of those I populations. So we have simple random samples of size n from I populations. So the total number of observations, big N, is little n 1 plus little n 2 plus all the way to like I, right? And if our null hypothesis is that all the population means are equal, the Anova test statistic has this F distribution with I minus 1 degrees of freedom from the numerator, and n minus 1 degrees of freedom for the denominator, right? So if I have, like with my flowers, my numerator would be 2 because it's 3 minus 1. And for the denominator, I'd need to add up the size of each of those samples and take away I. So take away 3, like taking away 1 from each population. Let's talk about Tukey, pairwise multiple comparison. So in the Anova setting, we have independent simple random samples of size in I from each of I populations that have normal distributions with means mu1 and common standard deviation sigma. Tukey's simultaneous confidence intervals for all pairwise differences mu1 minus muj among population means have the form: we take the differences plus or minus m star times S of P, where SP is our pooled estimate of our standard deviation, over the square root, right, of 1 over the sample size of group I over the sample size of group J. And our m star, it depends on the confidence level and the number of populations I and the total number of observations. So to carry out simultaneous tests of our hypothesis, we would let a mu1, mu I equal mu j, and then mu I not equal mu j. And for all pairs of our population at fixed significance level alpha equals 1 minus c, we reject the null hypothesis for any pair whose confidence interval does not contain 0. So a few more details of the Anova. We got like 4 more slides. We're so close. So the F statistic has the form where it's the variation among the samples divided by the variation among the individuals in the same sample. To find there we go. To find the measure in the numerator and denominator of F are called mean squares. If we call the overall mean response X bar, that is if we take the sum of all observations over N, that's going to equal N1 X1 plus N2 X2 plus ... So the sum of all the individuals divided by N, we're adding them up. Then we may measure the numerator by finding the I deviations of our sample means. So we take in the differences from the individual means of the samples. Then, lots of math. Okay, so then the mean square in the numerator of F is the average of the squares of these deviations. So I'm going to take N1 times X1 minus X bar squared plus N2 times the mean of X2 minus the overall mean, all the way on and on for no matter how big my sample is, divided by I minus 1. The mean square of the denominator of f measures variation among the individual observations in the same sample, right? So for all I samples together, we use an average of our individual sample variances, and we call it the mean square of error. So I'm going to take n1, the size of n1 minus n, times the standard deviation for that sample squared, and add that to the same part for our second sample, all the way through to our ith sample, where our MSE is over n minus the number of populations we're looking at over the total number of observations. So we're subtracting those two. So the Anova F test, right, is to test that all have the same mean, and F is actually the MSG, the mean square for groups, over the mean square for error, right? And this just repeats the same information I had told us in previous slides. We're looking at the difference, we're adding them up. And this is all in our text, but it's always nice to have another reference. Okay. So when our null hypothesis is true, F has the F distribution with I minus 1 and N minus I degrees of freedom. This is all things I mentioned before. The last thing I want to talk about is confidence intervals, okay? So to get an Anova confidence interval, what we can do is we get it for one of the means. So we take our estimate plus or minus T star times our standard error estimate. So we're going to use the population standard deviation from our sample to estimate this population standard deviation. So our confidence interval would be the sample mean plus or minus Ti times S sub P over the square root of Ni. Remember, this is our standard error estimate. And what we do is we're going to always choose our T value to be the bigger of the two, which would be the N minus I degrees of freedom.